Download this code from codegive.com, link in the description below. Diving deep into weak power scaling analysis and correcting common errors, Analysis 18. The error is weak power scaling. Analysis 18 often arises during the analysis of integrated circuits, particularly amplifiers, mixers, and similar components. It indicates that your simulation results, specifically the behavior of the circuit as the input power is varied, are not scaling as you expect them to based on ideal power-law relationships. This could point to several issues, including incorrect simulation setup, non-ideal behavior of components at specific power levels, limitations in your analysis techniques, or simply a misunderstanding of the expected scaling behavior. This detailed tutorial will guide you through understanding weak power scaling, common causes of Analysis 18 errors, and provide practical code examples, using Python with common scientific libraries, to analyze and diagnose these issues. 1. Understanding power scaling in ideal systems. Before delving into the errors, let's establish the baseline. How should power scale in ideal systems? Linearity. In a perfectly linear system, the output power is directly proportional to the input power. If you double the input power, add 3 dB, the output power also doubles, adds 3 dB. Mathematically, P_out proportionality P_in. Compression, gain compression. Real-world systems deviate from linearity, especially at higher input power levels. Gain compression occurs when the output power increases at a slower rate than the input power. The gain decreases as the input power increases. Think of an amplifier saturating. Intermodulation distortion, IMD. When multiple tones are applied to a nonlinear system, new frequencies, IMD products, are generated. The power of these IMD products scales differently with input power than the fundamental tones. For example, the power of a third-order IMD product, IM3, ideally scales as the cube of the input power. A 3 dB increase in input power results in a 9 dB increase in IM3 power. P_IM3 proportionality P_in. Harmonic distortion Similar to IMD, harmonic distortion introduces multiples of the input frequency. The nth harmonic power ideally scales as the nth power of the input power. P_harmonic_n proportionality P_in. 2. Common causes of error is weak power scaling. Analysis 18. Here's a breakdown of why you might encounter this error. Insufficient simulation range. This is the most common culprit. You're not sweeping the input power over a wide enough range to clearly observe the scaling behavior. Your simulation might be covering only the very linear portion of the device, where the power law is not yet apparent. You need to go deep enough into the nonlinear region to see the characteristic curves. Inadequate simulation resolution, step size. If your input power sweep has too few points, you won't be able to accurately fit a power law curve to the data. You need enough data points to robustly model the power scaling. Numerical issues and convergence problems. At extremely low or extremely high power levels, simulators can struggle to converge. Very small signals might be lost in the noise floor, while very large signals can cause extreme nonlinearities that break the simulator's assumptions. Consider adjusting simulator tolerances or convergence options. Incorrect measurement definition. You might be measuring the wrong parameter, or calculating it incorrectly. Double check that you're measuring the actual output power, or IMD power, or harmonic power, and not something else. Imperfect test setup / simulated environment. In real-world testing, mismatches, losses in cables, and other imperfections can affect the power scaling. The simulation must account for these elements if the real-world setup is being modeled. Component limitations and models. The simulator models used for your components might be inaccurate at certain power levels or frequencies. This is especially true for models that are simplified or don't fully capture nonlinear behavior, example simple diode models versus more advanced diode models with self-heating. Self-biasing effects. In some circuits, especially those with transistors, the DC operating point, bias, can shift as the input power changes. This can alter the gain and linearity of the circuit in a power-dependent manner. Frequency dependence. The circuit's behavior, and therefore the power scaling, might be frequency dependent. The scaling you expect at one frequency might not be valid at another. Presence of strong nonlinearities, mixers, frequency doublers. For circuits designed to be highly nonlinear, like mixers or frequency doublers, the power scaling of the desired output might not follow simple power-law relationships. You need to understand the specific behavior of the circuit and measure the right output signal, example the if frequency in a mixer. The error might be stemming from attempts to apply linear amplifier power scaling rules to an inherently nonlinear circuit. Harmonics and mixing products interference. Harmonics and mixing products that were not properly filtered out may interfere with measurement. 3. A practical approach, Python-based analysis and diagnosis. We'll use Python with NumPy, Matplotlib, and SciPy to analyze simulated data and diagnose weak power scaling issues. Example scenario ** Assume you've simulated an amplifier with an input power sweep and have obtained data for the input power, dBm, and the output power, dBm. We'll explore how to analyze this data to identify potential problems. Explanation of the Python code *. 1. Import libraries * imports the necessary libraries for numerical calculations, NumPy, plotting, Matplotlib, and linear regression, SciPy. 2. Sample data * This is critical. Replace the placeholder pin_dbm and pout_dbm arrays with your actual simulation data. The pim3_dbm example is commented out because you'll only have that if you simulated IM3 products. 3. Visualize the data * plots the input power versus the output power. This gives you a visual indication of the circuit's power transfer characteristic. Look for linearity, compression, and saturation. 4. Calculate gain * computes the gain, in dB, by subtracting the input power from the output power. Plotting gain versus input power helps identify the linear region and the onset of gain compression. 5. Linear regression and gain compression *. Select linear region *. You must carefully choose the region of your data that appears to be approximately linear. This is where the linear regression will be performed. Adjust linear_start and linear_end accordingly. This choice dramatically affects the accuracy of your compression point calculation. Linear regression * performs linear regression on the selected region to determine the slope, which represents the gain in the linear region, and intercept. Linear fit * creates a line representing the ideal linear behavior based on the regression results. Compression calculation * calculates the difference between the actual output power and the linear fit. This is the amount of gain compression at each input power level. 1 dB compression point * finds the input power at which the gain is compressed by 1 dB. 6. IMD analysis, optional if you simulated IMD products, example IM3, uncomment this section and replace pim3_dbm with your simulated IM3 power data. It performs similar linear regression and plotting to analyze the IM3 scaling and compare it to the ideal 3x slope. 7. Harmonic analysis, Optional, follow the same pattern as IMD analysis if you have harmonic distortion data. 4. Interpreting the results and troubleshooting. After running the Python code, with your data, analyze the plots and the printed regression results. Linearity is the data mostly linear over a significant portion of the input power range? If so, error is weak. Power scaling analysis 18 is likely due to an insufficient input power range or a very linear design. Gain compression. Does the gain drop significantly as the input power increases? The point at which the gain drops by 1 dB, the 1 dB compression point, is a crucial performance metric. IMD/harmonic scaling. If you have IMD or harmonic data. Is the power of the IMD/harmonic products increasing with input power, as expected? Does the scaling follow the expected power law, example 3x for IM3? Deviations indicate non-ideal behavior. Troubleshooting steps based on analysis. 1. Insufficient simulation range. The most common fix. Extend the range of your input power sweep, both to lower and higher power levels. Make sure you're covering the region where compression is clearly visible. 2. Inadequate simulation resolution. Increase the number of points in your input power sweep, reduce the step size. More data points will give you a more accurate power scaling curve. 3. Numerical issues. Adjust simulator tolerances. In your simulator settings, try tightening the tolerances for convergence, example set smaller voltage/current tolerances. This can help with convergence problems at low signal levels. Initial conditions. For transient simulations, ensure you have reasonable initial conditions to help the simulator start correctly. DC solution. Make sure your DC operating point is stable and correctly biased. 4. Measurement errors. Double check ports. Ensure that you're measuring the power at the correct output port. Reference impedance. Verify that the impedance used to calculate power is correct, typically 50 ohms. Signal selection. If analyzing IMD or harmonics, make sure you're selecting the correct frequency component, example the 2 F1, F2 component for IM3. 5. Component model issues. Use more accurate models. If possible, use more advanced component models that capture nonlinear behavior, example a more detailed diode model. Consult the model documentation. Model validity. Be aware of the limitations of the models you're using. They might not be accurate at all power levels or frequencies. 6. Self-biasing. Examine the DC bias voltages and currents in your circuit as the input power changes. If the bias is shifting significantly, this could be affecting the gain and linearity. You might need to add bias stabilization circuitry. 7. Frequency dependence. Perform the power scaling analysis at multiple frequencies to see if the behavior changes. 8. Nonlinear circuit behavior. Understand the circuit. If you're analyzing a highly nonlinear circuit, example a mixer, make sure you understand how the signals are supposed to mix and which output frequency you should be measuring. Filter appropriately. Use filters in your simulation setup, or in your measurement setup, to remove unwanted harmonics or mixing products that can interfere with your measurements. Important considerations. Units. Always be consistent with your units, dBm, watts, etc. Simulation time. Transient simulations for power scaling can be time-consuming, especially at low frequencies. Ensure you're simulating for a sufficiently long time to reach steady state. Simulator documentation. Consult the documentation for your specific simulator for guidance on power scaling analysis, convergence settings, and model limitations. Asterisk real world versus simulation. Asterisk remember that simulations are simplifications of reality. Component tolerances, parasitic effects, and other real-world factors can influence the actual power scaling. By systematically following these steps, you should be able to diagnose the causes of error is weak power scaling analysis 18 and take corrective action to improve your circuit's performance or your simulation accuracy. Remember to carefully examine your simulation data, understand the expected behavior of your circuit, and use appropriate analysis techniques. Good luck.